Today we will discuss the valence bond theory. Valence bond theory proposed by Hitler and London, then it is modified by Pauling. Valence bond theory explains the formation of bond in a molecule. It considers the energy factors also. So in valence bond theory, clearly it is explained how the electrons are shared in between two atoms. It is mentioned it is by the overlapping of orbitals. In order to understand the energy changes or energy factors in the formation of a molecule, we can begin with the formation of hydrogen molecule. Consider two hydrogen atoms A and B approaching each other, having nuclei Na and Nb, and electrons present in them are represented by A and Eb. Now the electrons are at a large distance. If they are separated at a very large distance, there is no force of interaction. There is no force of interaction between these molecules. As they are approaching each other, that develops some interactions. We can identify two types of interactions: attractive interactions and repulsive interactions. So as the atoms approaches each other, some interactions will develop. We can identify it as attractive interaction and repulsive interaction. Which are the possible attractive interactions? It is the attraction between Na and Eb. It is the attraction between Nb and Ea. Na and Eb means nucleus of hydrogen A, hydrogen atom A, and electron of hydrogen atom B. Nb means nucleus of hydrogen atom B, Ea, electron of hydrogen atom A. These are the two attractive interactions developed. Now, repulsive interactions also will develop. Which are the repulsive interactions? It is the repulsion between Na and Nb, nuclei of A and nuclei of B. Repulsion between A and Eb, electron of A and electron of B. So as the atoms approach each other, the attractive forces will be more than the repulsive forces. Therefore, the system is going to more and more stable situation, as it is indicated here in this graph. In the graph, you can see the energy of the system is decreasing as the internuclear distance decreases. Means as the atoms are approaching each other, or as the distance between the atom decreases, what happens here? You can see energy of the system is decreasing. When they are at large distance, there is no interaction. We can take the energy as zero here, zero. And as they are approaching each other, the energy decreases, means it will be negative, less than zero, negative. And the energy decreases and reaches a peak value here. This is the minimum value attained, minimum energy state. And we can identify this minimum energy state as the bonded state. Here the energy of the system is minimum, and therefore we can consider it as the bonded state. And if you are trying to decrease the distance less than this particular internuclear distance, what happens? The system is going to an unstable state, or energy of the system is increasing. A sudden increase in the energy of the system. And here this distance between the nuclei is known as bond length. It is the case of hydrogen atoms. In the case of hydrogen molecule, the bond length is 74 picometer. So here it is clearly explained when a molecule is formed from atoms, there is a decrease in energy. So valence bond theory clearly explains the decrease in energy during the formation of a molecule. Now the second thing, overlapping of orbitals. How the orbitals can overlap? Which are the various possibilities? According to valence bond theory, chemical bonds are formed by overlapping of atomic orbitals. Two possibilities are there, direct or axial overlapping along the axis. That results in sigma bonds. Such bonds are known as sigma bonds. Direct overlapping of atomic orbitals or axial overlapping of atomic orbitals. That is known as sigma bond. Sidewise or lateral overlapping results in pi bond. And if the orbitals are overlapping sidewise or laterally, then the resulting bond is known as pi bond. Here we can see various possible overlapping. Two s orbitals. S orbitals are spherical in shape. When they overlap, that will be along the axis. Along the axis. So axial overlapping or direct overlapping. So SS overlap results only in sigma bond. Results only in sigma bond. It is an s orbital, it is a p orbital, s and p orbital overlapping, sp overlap. In sp overlap, the overlap is again along the axis or direct overlap that results in the formation of sigma bond. In the case of p orbitals, pp overlap, direct overlap is possible as it is shown here. That results in the formation of sigma bond. Direct overlap or overlap along the axis, you can call it as axial overlap, results in sigma bond. But in the case of p orbitals, sidewise overlapping also possible. Sidewise overlapping also possible. Here you can see sidewise overlapping. Sidewise overlapping also possible. This results in the formation of pi bond. Sidewise overlapping results in the formation of pi bond. Now you will get a clear idea about sigma and pi bonds here. When you compare the strength of the bonds, sigma bonds are stronger than pi bonds. Sigma bonds are stronger than pi bonds. Because of more effective overlapping, sigma bonds are stronger than pi bonds. Now here, we heard about the single bond, double bond, triple bond. In a single bond, the bond will be a sigma bond. That single bond is formed by direct overlapping of atomic orbitals. In a double bond, one bond is sigma bond and the other bond is a pi bond. And in a triple bond, one bond is a sigma bond and the other two bonds are pi bonds. One bond is a sigma bond and the other two bonds are pi bonds. But we know when these orbitals overlap, a bond will form. For the formation of bond, 2 electrons needed. Bonded pair, you have studied it. 2 electrons needed. One electron will be present in one of the orbital and the other electron in the next orbit. So when these orbitals overlaps, if there is formation of a bond, surely the orbitals carry an unpaired electron. Only if the orbitals are carrying an unpaired electron, then only the chemical bond formation is possible by overlapping of orbitals. So what is the requirement for chemical bond formation? Orbitals with unpaired electron. When orbitals with unpaired electron overlaps, chemical bond formation will take place. So if the valence shell of an atom contains two unpaired electrons, it can form two bonds. If the valence shell of an atom contains three unpaired electrons, can form three bonds. So number of unpaired electron determines the number of bonds. But you consider the case of carbon. What is the electronic configuration of carbon? 1s2, 2s2, 2p2. The valence shell 2s2, 2p2. 2s2, a pair of electrons. 2p2, two unpaired electrons. So carbon has only two unpaired electrons. So how many bonds are possible in the case of carbon? Your answer will be two. But in CH4, carbon form four bonds with a hydrogen. So carbon can form four bonds with the hydrogen, but only two unpaired electrons are available in carbon. How will you explain it? In order to explain such a problem, another concept is developed that is known as hybridization. Hybridization. According to above principle, the electrons will enter into orbitals of lower energy. That will fill fast. Then only electron filling will take place in the higher orbitals. So when you compare 2s and 2p, 2s is the lower energy state. So only after filling 2s, electrons will enter into 2p. According to Hund's rule of maximum multiplicity, when electron filling takes place in the orbitals of same sub-energy level, what happens? One electron enters into each orbital only after getting an unpaired electron in all the orbitals of same energy level, the pairing will occur. So the remaining two electrons in the carbon that will be present in two different p orbitals. So here two unpaired electrons are present. If you want to redistribute the electron pair in 2s orbital, the energy of the 2s and 2p orbitals should be same. Then only we can equally arrange the electrons in all the four orbitals. At present, it is not so. That is why the concept of hybridization is introduced. What is hybridization? Hybridization is the intermixing of the atomic orbitals of slightly different energies so as to redistribute their energies, resulting in the formation of new set of orbitals of equivalent energies and shape. Equivalent energies and shape. In the case of carbon, we have two types of orbitals, S and P. In the valence shell, 2s and 2p. There are energy difference between 2s and 2p. Therefore, only 2 unbound electrons are available. If you can intermix these 2s and 2p, and if it is possible to make a set of new orbitals of same energy, we will get 4 orbitals with the same energy and same shape. Then the total electrons, that is 4 electrons, 2 plus 2. 4 electrons will enter into each orbital, and you will get 4 unpaired electrons. Thus, it is easy to explain the bond formation in CH4. So, hybridization is the concept in which intermixing of atomic orbitals of slightly different energy takes place. And by this process, a set of new orbitals are formed, and they are hybrid orbitals or hybridized orbitals with the same energy and same shape. Hybrid orbitals or hybridized orbitals with the same energy and shape. That is hybridization. And is it possible to intermix 2s and 3p orbitals? No. There are certain conditions. The energy should not be, there should not be a large difference in the energy of the orbitals. They want to undergo hybridization. So this hybridization has some salient features and some conditions. So we can see the salient features and conditions. First, salient features of hybridization. The number of hybrid orbitals is equal to the number of atomic orbitals that get hybridized. If 4 atomic orbitals are undergoing hybridization, you will get 4 hybrid orbitals or hybridized orbitals. If 5 atomic orbitals are undergoing hybridization, you will get 5 hybridized orbitals. The number of hybrid orbitals is equal to the number of atomic orbitals that get hybridized. Second, the hybridized orbitals are always equivalent in energy and shape. Already we mentioned, we will get a set of new orbitals of same energy and same shape. The hybridized orbitals are always equivalent in energy and shape. The hybrid orbitals are more effective in forming stable bonds than the pure atomic orbitals. That is the third point. Already we mentioned sigma bond is stronger than pi bond. And in the overlapping of atomic orbitals, if hybridized orbitals are undergoing overlapping, the resultant bond is stronger than the bond formed by overlapping of atomic orbitals. So the overlapping of hybridized orbitals is more effective than overlapping of atomic orbitals. These hybrid orbitals are directed in space in some preferred direction to have minimum repulsion. Therefore, the type of hybridization indicates geometry of the molecule. Type of hybridization indicates the geometry of the molecule. Its orbitals hybridized orbitals, it is in order to minimize the repulsion between the electron pairs after the overlapping, these hybridized orbitals are directed in space in different directions. Therefore, type of hybridization indicates the geometry of the molecule. Or if you know the type of hybridization, you can tell what is the geometry of the molecule. When we analyze the examples, you will understand it clearly. Okay, important conditions for hybridization. The orbitals present in the valence shell of the atom are hybridized. Only the orbitals in the valence shell will undergo hybridization. The orbitals undergoing hybridization should have almost equal energy. So 2s 3p orbitals will not undergo hybridization, but 2s 2p orbitals can undergo hybridization. What is the reason? They are almost equal energy. Promotion of electron is not an essential condition prior to hybridization. After the hybridization, it is not necessary to promote an electron. It is not a compulsory thing to promote an electron to another orbital. That is not a necessity. Promotion of electron is not essential condition prior to hybridization. And the fourth one, it is not necessary that only half-filled orbitals participate in hybridization. For bond formation, half-filled orbitals needed, but for hybridization, that is not a condition. Vacant orbitals can undergo hybridization. Even filled orbitals can undergo hybridization. So all the orbitals in valence shell can take part in hybridization. There is no requirement of an unpaired electron in the orbital for hybridization. So I think it is enough for today, and the examples and other things we can see in another class.